in the truck. So number one, the table below shows the relationship between the number of miles driven with a U-Haul and the cost of renting the U-Haul. Okay, all right, I see that table. Looks good, looks good. A, what is the average rate of change in the cost of the rental between M equals 10 and M equals 25? So when you see this, we're going to abbreviate that. We'll start calling that AROC, average rate of change. Is there any like light bulb moments that are like triggering in your mind when you see that phrase? There'd be no, it looks like. Thomas Edison is not among us. Anyone? Okay, so here's what I want from now on. Every time you see average rate of change, this is what you should think. Do you guys know what a rate is? Like, give me a rate. Like real world. I'm off of this problem. Like real world rate. Okay, $10 per hour. You might think of another one. Okay, I just wrote 70 miles per hour up there. That was a good thought, though. You were right there with me. We're on the same wavelength. Miles per hour, dollars per hour. What do y'all think of when you see the word per? Okay. This is why I got to know. This is what we're finding out. Whenever you see per, I want you to think fraction. So if this is $10 per hour, that means I'm making $10 every 1 hour. 70 miles per hour would be the same thing. 70 miles over 1 hour. Rates are fractions, and we say it with the word per in pretty much every rate we have. That lets us know what's in the numerator, what's in the denominator. Well, so a rate is a fraction. Well, guess what slope is? It's a fraction. It's a rate. The rise over run. The change in y over change in x. Right? They go interchangeably. When you first learned about slope in 8th grade, you probably started it as an average rate of change problem. That was the beginning. And so that's what we're looking at here. So if I'm wanting to know the rate of change, I'm wanting to know the slope of the line given 2 endpoints. Well, how can I find slope or rate of change? That's it. So I need 2 points. If I know 2 points, I can find the slope. Do I know points? I know the x value, right? Well, if the x value is 10, guess what it gives me right here? The y value. X value is 25. I know the y value is 42.25. So I'm going to fill out this. This is called a difference quotient. I'll talk more about that in a second. So y2, I'm going to go 42.24 minus y1, 28.89 over x2, 25 minus x1, 10. On your AP exam, you're going to have one free response question that is you writing a difference quotient. You get credit if you write this. Man, that's hard. That's tough. It's so hard. And now then we're going to find this value. I'm just going to cheat. 13.35 over 15, which they found to be 89 cents. Well, it's not actually 89 cents. Let's talk about what it is. What's the numerator? What am I dealing with here?
13.35.
Yeah. But like what unit? What unit is the numerator?
Cost in dollars.
So this is money, right? Cost in dollars. What unit is the denominator?
Miles.
So if I had to make sense of this, what is this 0.89 representing?
89 cents per mile.
89 cents per mile. So you see that per? You see that rate? That slope? Yeah. Yeah. Okay, let's look at B. What is the average rate of change in the cost of the rental between M equals 25 and M equals 50? So what am I going to have to do here? Find the slope, right? Good. We learned it. You see A rock, average rate of change, find the slope. Boom. Automatic. So you guys can go ahead and plug that in. 64.49 minus 42.24 over 50 minus 25, which is, I'm going to cheat again, 22.25 over 25, which is
28.
if I want to give context, that's cents over mile, right? Or you could just write 89 cents per mile. Means the same thing. So what have we just discovered?
The 89 cents. Each mile costs 89 cents.
Okay. And is that forever? Is that for every
No,
value?
because 10 miles is $28. So there's an initial cost.
Okay, but we're not there yet. You're ahead of me. You're right, but that's not what the initial cost is going to be the same every time too when I get there. But whether I drove 50 miles or 500 miles, it's going to cost me 89 cents a mile after that initial cost. Okay? So what we have discovered, because I picked 2 points here and found the average rate of change, and I did it with 2 different points and found the same average rate of change, then that means the average rate of change is constant. So what does that mean? What do we know about this situation if we have a constant rate of change or we have a constant slope? It's going to be linear. It's going to be linear. It's the same, but if I were to graph this situation, it's going to be a line. Anytime my rate of change is constant, it's linear. Okay? AROC is constant, so graph is linear. Okay? That's one way we can discover if something is linear or not. And those steps should have been mostly familiar to you. Whether you tied it all together like that before or not, I don't know. All right, but here's another way. This is a really big deal in the AP Pre-Cal class. I'd never heard it explained like this, but the wording I'm going to use is very important because it's the way they're going to want you to answer a question if you get one like it. So let's look at our inputs. We want to look for equal changes in our input. So like right here, from 10 to 15, how much did my input change by? 5. So I want to see if I can find if it changes by 5 again. What about from here, from 15 to 25? I went up by 10. Okay, well that's not helping me much. What about from 25 to 40? Up 15. And then what about from 40 to 50? 10. So you can see here I went up by 10 in 2 different places that matched. So those are what we call equal changes in the input. The blue is where I'm up 10. Equal changes in input for the 2 plus 10s. I know you guys don't have color coding, so it'll be harder for you guys to make sense of that. But have equal changes in the input at the plus 10s. So I want to go and look at the y values in that same situation where I went up by equal changes in the input. So look here, I went from 33.34 to 42.24. So how much did I go up? Can y'all do that in your head? Okay, let me ask you this. What if this was $42.34? $9, but we're not quite there. We are, yeah, you see how you can do that in your head? Yeah, $8.90 up. I'm gonna make y'all mental mathematicians before long. It'll happen. So I went up $8.90 on that interval. If this is linear, I should have the exact same amount I went up by here in my other plus 10. Okay? So let's check here from 55.59 to 64.49. How much did I go up there? $8.90 again. And so then here's our big note. I'll do it over here. And again, this is the one I never used this wording before I taught the class last year. Equal changes in input produce equal changes in output so the function is linear. Do we understand what I'm trying to say? The 2 places where the x's went up by 10, the y's went up by $8.90. So because of that, it's a line. So I've shown you 2 ways to find it was a line. We found the average rate of change. Do I need to, can you guys, we got that written down yet? Before it goes away. Okay. Okay, 2, graph the points. So again, it's going to be a approximate graph. Let's see, we know at 10, we should be at 28.89. At 15, we should be at 33. At 25, we should be at 42. That's 20, Cody. At 40, we should be just above 55. And at 50, we should be at 64. 50. So what can we say about these points? I kind of have already talked about it. It's linear. If you did a good job drawing your points, which I didn't do great, but so we could say the points make a line. So the cost per mile, the y over the x, right? Cost per mile, slope is, so let's put slope in parentheses. Slope is constant. The points make a line, so the cost per mile or the slope is constant. So again, if I have a constant slope, that's the same thing as saying I have a constant rate of change. Means the same thing. Oh gosh. Okay, here we go. Here we go. You ready? Everything we've done so far has been pretty much review. We haven't done anything that's supposed to be pre-cal level yet. Right? It may be some stuff that you didn't know or hadn't put together, but we haven't done anything that's like earth-shattering, groundbreaking, new. Here's your first, I would say, new thing. 3. Is the rate of change of the cost increasing, decreasing, or staying constant?
Staying constant.
Yes. How do you know?
Because it is in one. It's linear.
That's it. It's staying constant. Is everybody okay with that? And so then explain, I would say, on any interval, like how I was about to say interval, so I said inti instead of. The rate of change is 89 cents per mile. Okay. Okay. Are we ready? Are we ready? Are we ready? So right here, we just said the rate of change, which is how much this graph is changing by. We said the rate of change was 89 cents per mile. Everybody's okay with that? It's linear. And then you said it was a constant rate of change. So then what is the rate of change of the rate of change?
So this one would just be 1 because it's constant.
No. That now you're in pre-cal. That's the pre-cal level. Rate of change of the rate of change. So what was the rate of change here in this situation? 89 cents a mile. What was the rate of change here in this situation? So how much did my rate of change by between here and here? It didn't. So the rate of change of the rate of change is 0. And that's always going to be the case when it's linear. The rate of change of the rate of change is 0. What we're doing is we're preparing you to do calculus without any of the tools to do calculus. This is a big deal in calculus, taking derivatives. We got to know what it is, but if I took a derivative of a linear function, I would get the slope. If I took a derivative of the slope, I would get 0 every time, which is this is the idea behind it, is the rate of change of that rate of change. And if we have time, I might show you a little bit about derivatives and that stuff.
Excuse me, teachers. 7th graders, last name A through L, please go to the library at this time to pick up Chromebooks. 7th grade, last name A through L, please go to the library to pick up Chromebooks.
Okay, another idea that we need to mention, and I think I'm going to do it right here before we finish 4 and 5, is the idea of a secant line versus a tangent line. Okay? And again, this is a calculus idea. Have you guys heard of secant lines and tangent lines in geometry? It's probably when you last heard about them. You probably heard secant and tangent last year in Algebra 2, but you didn't talk about secant lines versus tangent lines. You do that when you talk about circles. So anybody remember? It'd be okay if you don't. I wouldn't have remembered from then. Okay, so let's talk about it with a circle, and then we're going to take that conversation onto a graph, because a line is a dumb thing to start with. This just going to break your brain. Okay, so you said it's already broken? Is that what you said? Yeah, that's okay. I have that effect on people for whatever reason. Okay, if I had a circle and I was going to draw a line that intersected the circle twice. We have an intersection here and here. This is called a secant line because it has 2 places that it intersects the circle. If I have a line that's basically on the outside of the circle, but it does intersect it at one point, this line is called tangent to the circle. So essentially, a tangent line touches the graph in one spot. A secant line touches the graph in 2 spots. No, I said that right. Tangent line 1, secant 2.
I remember this now.
Vaguely?
Yes.
And you probably would have turned this into chords. But again, you don't spend a lot of time there, but you're supposed to briefly mention it. So let's talk about a parabola, okay? Because a parabola is going to be more interesting to talk about than a line is here. If I wanted to find the average rate of change, so let's think about it. Let's just do half a parabola. That way I can kind of explain the situation. Let's say we're here. And so let's say my y value is speed and my x value, you don't have to write this down if you don't want to. If you guys can just follow, I want you to think. Speed for the y value, and let's say the x value represents time. So say I wanted to know between this point and this point, what was the average rate of change of the car? Okay, average rate of change. Well, I could find the average rate of change. It's just the slope of a line through those 2 points. So let's just say I know these. Let's say that this red point, the first one, is the point 1, 10. And then let's say this point is 6, 60. So what would the average rate of change of the... It would be 50 over 5, which is... So let's change this. I don't want this to be speed. I'm gonna break. That's gonna break my brain. Let's change this to be distance. So let's say that like this car was driving in a straight line, right? And I had it marked. After 1 second, it was at the 10-yard line. I know there's no 60-yard line, but let's just go with it. And then after 6 seconds, it's at the 60-yard line, which means between these 5 seconds. From 1 to 6, it traveled 50 yards, which means it was going an average of 10 yards a second. We follow that logic? Now, was the actual speed of the car 10 yards a second? No. The whole time through there? No. But that was the speed that it averaged between those 2 points. So if I wanted to find, this is average rate of change. If I wanted to find its actual speed at any given point, let's say like right here, at this point, do you think the car was going faster than 10 or slower than 10?
Faster.
What about at this point?
Slower.
Can you see that? Okay, you can see it graphically, and you're correct. It was slower here because it was slow ramping up, but as it distance started growing more quickly, that means it was going a faster speed. So what we wanted was an instantaneous rate of change, which is a tangent line. So let's pretend like right here at this point, I wanted to know, what was its speed here? If I could find a tangent line to the graph, right? Tangent means it touches the parabola once versus twice. Then the slope of this black line would represent the actual speed at that point. Versus the red line is an average speed over an interval. If I wanted to approximate and get closer and closer to the actual speed, I could take that red line and I could shorten the distance between it. So instead of going between 1 and 6, let's say I went between 5 and 6. Can you see the secant line between the purple points? It's going to have a greater rate of change than the red line, which means we're closer to the actual speed at that given point, but it's still slower than the actual speed. See, it's still slower than the black line. And when I say slower, I'm talking about the slopes of the lines. Those represent speed, right? Because it's a distance over time. It's a y over x, which is slope. It was getting up to speed. Just give it time. Okay? Yeah, I mean, it's not a very good 40 time. It's not very good. So the moral of the story here, do you guys know thinking about so like used to in big cities, you know how hard it would be if you guys you're probably too young to have driven through the middle of Atlanta because it's a dangerous place. Have you ever ridden through the middle of Atlanta?
Yes.
When 75 and 85 merge and there's 20 lanes and people just go as fast as they want because there's no way a cop can get you because it's a disaster in that area. Anyway, so there's about 20 lanes as soon as they merge in the middle of Atlanta. 2 interstates, 75 and 85. It's a disaster. I drive to Orlando a lot, so I've been there. 20 lanes in one direction.
Yeah, I get what you're saying. That's crazy.
We'll look it up. It's probably not quite 20, but it's over 10. It's over 10. So a way that we could police speed in that area, if I was the cops, we could put 2 lines on the road that are a mile apart. And I could be at a helicopter above the city, and I could look for a car and start the stopwatch here And then in the stopwatch here, and let's just pretend like it's 60 miles an hour. That's the easiest one to do math with. Let's say, so if it's 60 miles an hour, how long should it take them to drive 1 mile? You guys know?
1 minute.
1 minute. A mile a minute if it's 60 miles an hour. So let's say that we time them, and it took them exactly 1 minute to go between those. So were they speeding?
No.
They weren't speeding over that whole interval, but am I sure they weren't speeding? Oh boy was driving 200 into the area, and then he decided to get off and stop for a minute, and then said, oh, I'm in trouble. So he waited on his time, and then he got back on. So I can't be for sure he never went over 60 in this interval, but his average speed in this interval wasn't 60. So how could the cop do a better job of finding what his speed was instead of doing this?
Sensors that tell you your speed.
Okay, which is like a radar gun. Do you guys know how a radar gun actually works? Do you know the workings of a radar gun? But it gives you your speed a lot closer than over a mile distance. Right? Cops don't have to wait a mile to figure out how fast were you going. They can figure it out almost like that. Because what a radar gun does is it sends 2 beams out very quickly. As quick as you can between 2 points. And then those signals then return back to the radar gun. And so then the radar gun can figure out how far, what was the distance that the beams traveled, because it's going to be a shorter distance if it's getting closer to me, right, over that short time. So you can figure out the distance the beams traveled when they returned over the time it took, whatever the time difference is between them. So say the time difference is 1/10 of a second. So what was the distance the car traveled? It would be so many feet over 0.1 second. That's really close to instantaneous. So what the radar gun does, essentially, is it gets 2 points very close to the same time that it almost is your instantaneous speed. Right? It does a slope formula of 2 points that are so close to each other that it's basically a tangent line. We take the secant line and get as close to a tangent line as we can. Well, I'm trying to be entertaining. All right. Sorry if you guys hate me already. Okay, where is my pencil? Pencil. There. Thanks. Let's just keep going. 4. U-Haul charges all of its customers a minimum base price regardless of how many miles they drive. What is this base price? This is the initial price that Cam was talking about originally. It's what?
$19.99.
How did you figure that out?
28.89 minus 8.90.
That is correct. So we know after 10 miles, I'm getting charged $28.89. But if I can subtract those 10 miles off, so how much was I getting charged per mile for those 10 miles? I was getting charged 89 cents per mile. I could take that value off, which is the $8.90 that Cam said, right? Which is essentially just 10 miles at 89 cents a mile. And if you do that, you'll get $19.99. And so how did we do that? We took the cost for driving 10 miles and subtracted it for every mile that we drove, those first 10, to get $19.99. Where does that show up graphically? The base price. The y-intercept, when the x value is 0. So you can see here, even on our rough graph, we were just below 20. We were probably closer to 19 than 20, but it's we didn't have a very good scale to do that graph anyways. But it's still, I can say I'm in the ballpark. I'm right where it should be, somewhere in that area. Okay? So if I had to write an equation for the cost of renting a U-Haul and driving it for M miles, so C of M is going to be equal to, so we know the relationship is linear. So how do we write linear equations? 0.89. We're going to use M instead of X just because they ask us to. 0.89 M plus 1999. I was looking for slope-intercept form, right? We knew the slope was 0.89. We found the y-intercept was 1999. And so this would be the equation of that situation. So here's the notes for the lesson. Linear functions have constant rates of change. And then each equal interval of the domain produces an equal change in the output. Remember that big fancy wording I wrote out on the right side? Told you this is going to be a big deal. That is the wording that they are going to use. So because the rate of change is constant, that means I have a linear graph. Rate of change is constant, linear graph. Then that means the rate of change of the rate of change is 0. And then they say here, lines have no concavity. We've not talked about concavity yet. That's going to be coming up in the next week. Okay? So we'll talk about concavity when we get there, but that's going to be a big idea as we go. And then big idea 3, the slope of a line represents the constant rate of change. So that's what we said. Anytime you see rate of change, think slope. You see slope, think rate of change. They're used interchangeably. If my slope is positive, that means the quantity is increasing. That's what that says there. If m is greater than 0, if the slope is positive, we're increasing. If the slope is negative, the quantity is decreasing. So in our U-Haul problem, the slope was positive because the prices kept going up, right? It was positive 0.89.